Lovely. Light is on. Ooh. Okay, how about now? Yes? Okay, I have always, I guess, had this potential of working in a call center. Now with this thing in front of me, I feel like I am achieving my potential. We'll see how this goes, right? It's one of these things. It's not quite as bad as the new iPhone earbuds, but it is likely to fall off. We will see. All right. Happy October. Announcements, as usual. No surprises, including the fact that this doesn't work. Right, you've got a project deadline tomorrow. Homework due this week as usual. Midterm, you know when it is. This week, we're going to be doing hypothesis testing. Next Monday is, I'm yet to decide whether I will do a lecture of examples or whether we'll have a special lecture. We're trying to work something out. Wednesday of the following week will be a review. Lab of the following week will be review. And then Friday you have an exam. Sometime late this week, we will send out some practice materials for you to work on. And if you've been doing... Oh, thank you. That's great. Excuse me a moment. I am going to switch media. Okay, we're doing the other one. All right, let's get this going. I must have some weirdly shaped ear. That's all I can conclude. Okay, I'm going to give the entire lecture holding on to my ear. I am reminded of a cartoon that came out when the iPhone first became popular and people were taking pictures on it. There was the person was of my generation, and they had the phone to their ear, and they were telling somebody, I think I just took a picture of my ear. And that's me. Can you hear this? It's not worth hearing, but can you hear it? All right. Okay, we're going to try. This feels seriously weird. Yeah. Is that more call center-like? Yeah, kind of. Okay. It's pink. It's bizarre. All right. Right. You know what a statistic is? A statistic is a number calculated from a sample. Key point about a statistic: it depends on the sample. Therefore, it could be different depending on how the sample comes out. You have one sample, you will have a statistic calculated from that one. What you have to do is imagine all the other ways it might have come out. And we have a tool that helps us with that imagination. And so what we did last time was we were able to simulate this thing. If we knew the population from which this sample was going to be drawn, then we could repeat the sampling procedure over and over again. Draw a sample, calculate the statistic. One value. Then, if you know what the population is, you can draw another sample, and you get another value of the statistic, and so on. And so you have a very clear idea of how much and in what way that statistic can vary. And what we're going to do today is to use that idea in your first inference problem. And what we're going to do is we're going to study a report by the ACLU, the Civil Liberties Union of Northern California, about racial and ethnic disparities in Alameda County jury pools. And it's available online. There's a link to it in your textbook. It looks like that. Do you recognize that? Where is that? Oakland, yes. What's that lake called? Lake Merritt. Okay, all you Berkeley people. It's a little bit to the south. It's actually lovely. Go. So this is a report, and the basic idea is this. They studied jury selection in Alameda County, and there was a conclusion that certain ethnic groups are underrepresented in jury panels. And so what we're going to do is we're going to examine how juries are selected, and we're going to look at the data and see what we conclude from the data. And so the first thing I want you to do is for you to understand very clearly exactly how juries are selected. Okay. So you know, I think, that there's a population of eligible jurors. Does anybody know what you have to satisfy to be an eligible juror? How old do you have to be? 18, and you got to be a citizen. Very good. 18, citizen. Any other criteria that you know about? English skills. You have to be able to communicate in English. So that's 3. Any more? No criminal record. Yeah, almost. Felony. If you've had a felony conviction, that's a problem. And so on. So there are numerous criteria that you have to satisfy, and then you are a member of the eligible jurors in your county. You have to be a resident of the county in which you are called. And from this, a jury is selected, and we all have this sense that, it's a jury of our peers. Somehow there's a random selection that goes on. And what we need to understand is very clearly exactly where that randomness is. So from eligible jurors in the county is created a list of these people. And from the list of eligible residents, a panel is selected, and a panel is not the 12 people on the jury, but it's, of the order of 100 people, and here is where the selection is supposed to be random. So about 100 people are called in for any jury trial, and then the 12 people are actually selected in a manner that is not random at all and perfectly allowed by law. The judge can make allowances for medical reasons for some people, so they don't serve. Lawyers on both sides are allowed what are called peremptory challenges. They can strike people without giving a reason, some number. Then the remainder have to fill out a questionnaire. Then everybody fills out a questionnaire, and the remainder of the questionnaires are looked at, and between the judge and the two attorneys on both sides, they come up with the 12 people. So there is no randomness from here to here. It is very deliberate. And there are laws that determine in what way the selection can be made from here to here. But it's here, this panel, that is a large set of people from which the ultimate 12 people are going to be selected. That is where the randomness comes in. And there is a law. You've got California's Code of Civil Procedure. All persons selected for jury service shall be selected at random from a source or sources inclusive of a representative cross-section of the population of the area served by the court. Okay, so here, for us, is a very interesting phrase, at random. We're rather good at that. And so what we're going to do is we're going to take a look at the data and see if the data bear out that, in fact, the people who are selected are somehow random. And so what I'd like you to do is just take in a few details of what the ACLU did. In 2010, it collected panel data from 11 trials. So it's collecting data on these people. These are the people that are supposed to have been selected at random. And the number of people in those panels was approximately 1,500 total. 11 trials, about 100 people per trial, so 1,500 people is roughly. 1,453 was the number on the panels. And what they did was they looked at the ethnic composition of those 1,453 people as compared to the ethnic composition of the eligible jurors. And so that's what we're going to do. We're going to look at these two distributions and see whether they look the same or different. Okay? And we've been kind of doing this for a while. We've been looking at this distribution, kind of looks like that one. And so today we're going to do that more carefully and try to answer some questions that were raised in this report. Okay, before I go on, are there questions about the jury selection? Is it clear why we are looking at the panels and not the ultimate juries? Yes? Because it's the panels that are supposed to be selected at random. And the total panel size of 11 trials is approximately 1,500 people. That's our sample, if you like. Okay. So here are the data. The table called jury contains 3 columns. One is the categories. The second is the proportions in the eligible population. I'll have a lot to say near about the end of the lecture about where these numbers come from. And then these are the numbers in the 11 panels. So among the 1,453 people, those are the distributions. And so naturally, if you want to compare, so the ACLU report said that Black and Latino jurors were underrepresented, and it certainly seems to be the case from looking at this. However, these are groups that are supposed to be selected at random. So if you select at random from the blue distributions, you don't expect to get exactly the blue distribution, do you? It's going to be a little bit off. So the whole question now rests on, well, is it, off like a random sample would be off? Or is it off in some other way? Okay, that's the question that we're trying to answer. So now the first thing we're going to do is we're going to quantify this word off. Because right now we're looking at these two distributions and say, well, the gold distribution looks kind of different from the blue one. But kind of different doesn't help you when you're actually trying to measure something. So what we're going to do is we're going to get a measure of the difference between two distributions. When you have two numbers, you know how to measure the difference between them. It's just a minus, and sometimes you take an absolute value. But now we have distributions. So we have this set of numbers that adds up to 1, and we are going to compare it to this other set of numbers that adds up to 1. And there's a correspondence because the pairs are linked. So surely the natural thing to do is to just do a minus. Yes? Where are the minus signs in the difference? Which rows? Black and Latino. That's the first thing that the ACLU is observing. That's what the minus signs are. And so what does the minus sign mean? That means the panel proportion is smaller than the proportion of eligible jurors. So now we are going to use those differences to develop our measure. And here's a little exercise that I want you to do. Calculate two quantities in your head. Some of the differences are positive and some are negative. You agree? Yeah? Add the positive differences in your head, and also please separately add the negative differences. The sum of the positive differences is how much? 0.14. The sum of the negative differences is how much? Minus 0.14. So if you just add up all the differences, you're going to get 0, right? This makes sense because you are looking at the difference between two distributions. The gold bars and the blue bars both add up to 100%, both add up to 1. So the amount by which the gold bar exceeds the blue bar is exactly the same as the amount by which the blue bars exceed the gold bars. So simply averaging the differences will give us 0 no matter what those two distributions were. And so while the 0 is correct, for our purposes it is totally useless. In fact, it seems that the 0.14 by itself is a measure of the distance between the two. Right? You get these two equal measures of differences. The 0.14 by itself is what we like to calculate. And so now you can imagine if you're given two distributions, you can go through, compute the difference, find the differences that are positive, and then add them up. Yep? It's a little more efficient to notice that you can find, you can drop the signs of everything, add the whole lot of those absolute differences. What do you get? You'll get the 0.14, and then instead of a minus 0.14, you'll get another 0.14. Yes, so you'll get 0.28, and what you want is that divided by 2. Yes? So you can arrive at the 0.14 without doing a check of where the differences are positive. You simply take the absolute value of all the differences, add the whole lot up, and divide by 2. That is called the total variation distance between the two distributions. And look, it comes out to be 0.14, which is what we wanted in the first place. Okay. So look what we've done. We have taken the absolute difference column, we have added it up, and we have divided by 2. That is a measure of the difference between two distributions. So total variation distance, you have essentially a recipe, which in other classes is called a formula. For each category, compute the difference in proportions, take the absolute value of each difference, add the whole lot up, and divide by 2. And those of you who are mathematically inclined should know that it is well defined as a distance. There's a concept of a distance in mathematics. It's a perfectly good distance and a powerful one for answering some questions. Okay, so what we have is a distance between these two distributions, and it's a number, and that number is 0.14. That's terrific. But we have no idea whether that 0.14 is big, small. We have no idea of a scale for that 0.14. So to understand that 0.14, it's important to compare it with something else. Right? So we're going to compute the total variation distance between something and something else. In other words, we're going to compute total variation distance a lot of times. And when there's a move that you're going to make a lot of times and you've got a computing system in front of you, then what do? You write a function. You write a function to do it so that you don't have to keep doing the calculation every single time. You just call your function. And so we have written for you two functions. The first one, called total variation distance, takes two arrays and returns the total variation distance between the distributions in those two arrays. And the second one takes a table and assumes that you have a column label that contains one of the distributions, another column label that has another distribution. It calls your previous function and returns the total variation distance between the distribution in the first column here and the second column here. Please take a look at those two very short definitions and see if you have questions. The first one is essentially what we did before, and the second one just calls that on columns of a table. And so our data are in the table, well, I mean, if we go back, here's the table jury. If I call table TVD on this table and say table TVD of jury, this column versus this column, table DVD apply to the table jury, eligible column versus panels, what should the answer be? It's on the screen. It should be 0.14, right? We're basically repeating the same calculation that we've done before, and it's 0.14. Okay. Terrific. So what we have now is a function that will compute total variation distance given a table and the two column labels that you want to compare. That's going to be handy. So now we're at the question of this 0.14. Is that a big difference? Is that a small difference? Well, to talk about big and small, these are relative concepts. And so you have to have something to compare with. And to decide what you have to compare with, it is important to go back to the original question. What was the original question? We've done so much now that we've lost the original question. What was the concern here? Excuse me? Yeah, could this difference, could this be a result of randomness, or is it something else again? So exactly, the issue is how does this compare to a panel that would have been drawn at random? Right? If it looks kind of like that, then, well, there's nothing really more to say. It's randomness. But if it doesn't, then maybe we should examine things a bit more closely. Okay? So if we are going to compare this distance to panels that have been drawn at random, what do we now have to do? So we'll talk to your friends and devise a plan. Right, what do we need? A key item that we need is what? Did you just talk to your neighbor about what you did over the weekend? All right, tell me something that we need here. Not code, concept. I'm sorry? A simulation. Okay, of what? What function? Total variation distance between what and what? See, what all of you are doing is you're going right to the... This is not my friend. You're trying to get way ahead and getting deep into the weeds of the computation. What's the fundamental thing that you need to compare? You have a set of 1,500 people, 1,453 actually, on this panel. You want to compare to what? You take, okay, so stop. Not too many steps, just one step. You take another sample from the eligible jurors. That is a key idea. You take another sample. How? At random. There you go. The fundamental thing that you need is a random sample from the eligible population. You are going to compare your 1,453 people to this random sample that you draw from the eligible population. Everything else is detail. So you need a random sample from your eligible population. Thank you. To that random sample, so you'll get, by the way, how big should that random sample be? Same size as the panels, which is 1,453. So when you draw at random from your population, you will have 1,453 people. What do you have to do with those people? Sort them by ethnicity. That's what you have to do. So you need to compute the proportion in each of these categories that your new random sample is in. Then you have a new distribution, and you can compare total variation distances, right? So we need a method to draw at random from this eligible population. So take a look. What does the eligible population look like? What we are given is categories and proportions. We have to draw at random from this. And what I would like to discuss is we have drawn at random before. We have drawn at random a couple of different ways. Can somebody remind me of one method that we've used to draw at random? We've used two. Sample, dot sample, right? That operates on a table. And what does it do? It draws rows at random with replacement. Is that what we want to do here? If I do dot sample from here, well, actually, is this helpful? We do not want to sample the categories. We want to sample people. Yes? Not helpful. Okay, that didn't work. What's our other method? np.random choice. That operates on what? An array of individuals, yes? And it gives us back some subset of those individuals. So, can we use that? Not from this table, we can't. Because if we sample from this array, what numbers are we going to get back? We're going to get back numbers like 0.15, 0.18, etc. We are not going to get white and black and Latino and Hispanic and other. Right? So basically what we're realizing is we don't have a method. The two methods that we have for drawing at random do not work in this case. We need a new method. And so we have a method that we've written for you. What it will do is, so you see these numbers, they all add up to 1, yes? Think of them as just percents, and so 15, 18, 12, 54, and 1. Those numbers will add up to what? 100, and essentially what's happening is in the background, an array of 100 people is being created. 15 of them are labeled Asian, 18 of them are labeled black, etc., etc., etc. And then you are choosing at random with replacement from that array. How many times? About 1,500 times, the same number of times as the panels that we have, right? Then you will get a list of 1,453 labels, which you can then sort into the different categories and compute proportions. Now, in theory, you know how to do all this, yes? You know how to create this array, you know how to do np.random.choice, you know how to group to get into the different categories, and you know how to return proportions. So rather than have you do that every single time, there is a little function called proportions from distribution that just does all that. No mystery to what it is doing whatsoever. It just saves you a bit of grief. So the panel size, I'm just going to call that panel size just because I don't want to carry the number 1453 around all the time. So what we are going to do is we are going to call proportions from distribution on our table, and it takes 3 arguments. It takes the name of the table, obviously, the label of the column that has the distribution from which you are to draw the sample. So we must draw a sample from the population of eligible jurors, after all. And it has to say how many you want to draw. So it has sample size. And what it does is it returns a new table, which we are going to call panels and sample. And I'd like you to stare at those numbers for a bit. The first 3 columns came from the study. So there's the distribution. These are the ethnicities that were used. This is the proportions among the eligible jurors. These were the proportions in the panels. And here's our random sample. So now we're going to compare all of these 3 distributions. It's a great idea to draw a bar chart, and there you go. Take a look and talk to your neighbor about what you see. All right, ladies and gentlemen, what do you see? Just to be clear, the blue and the gold are what they were. We now have a gray one. That's the random sample. Yes? And we are comparing what to what? So we first compared the blue to the gold. Yes? The eligible to the actual panels. That was our base data, right? What's the next interesting comparison? The blue with the gray. The eligible jurors compared to a random sample from that eligible population. Yeah? And when I look at this, the blue and gray look very similar. Very similar compared to the blue versus the gold. Yep? So if I just stick with this one random sample, my sample in the panels is not looking like a random sample. You all agree? So now we're here, and we're seeing something. We're picking up what the ACLU noticed here, but we are data scientists, and so the next question the next point we are going to make is what? Does it happen all the time? And so, here had somebody suggested a for loop. You had suggested doing it over and over again. Maybe we just got lucky with this sample. Maybe this sample just came out looking exactly like the population by chance. Let's do it again. And this is why we spent the past couple of lectures doing this, drawing samples lots of times, computing a statistic and see how much it varies. So we are now perfectly poised to simply do that over and over again. Yep. So we're going to simulate the total variation distance. Okay, so now every word matters. We are going to simulate the total variation distance, affectionately known as the TVD, between the distribution of eligible jurors and a random sample from that distribution. All right, we know how to code. We're going to code. Actually, why don't we just see what this total variation distance came out for this particular sample. So we have a function that we just wrote, table.tvd, a table tvd, and it takes the table name and the two columns that contain the two distributions you want to compare. So if we want to compare the eligible distribution with the distribution of the random sample, then it's table tvd, table name, and the names of the two columns that we're trying to compare. And I wonder what we got here. We got 0.007. What had we got before? For our eligible versus the panels, it was 0.14. So you're looking at 0.14 versus 0.007. One of them is a lot smaller. Which one is it? The 0.007 is a lot smaller, right? So it is a good idea, actually, to see if we can run this thing again. A little bit off here. Okay, so the 0.007 became a 0.023. What did we have before? We had 0.14. Right? So what you're saying is that your random sample isn't always exactly like the distribution. The random sample does vary. And so, naturally, this is now incentive to do lots of random samples, compute all the TVDs, and draw a histogram. All agreed? That was kind of the purpose of the past two lectures, to set us up for this. And so here we are going to compute the empirical distribution of the total variation distance. I'm going to tell you, I have taught this subject for decades. And standing in front of a class where there are many, many freshmen and using terms like empirical distribution and total variation distance is just such a joy, because this isn't taught anywhere. Some of you who have taken AP Statistic will be mentioning things like chi-squared in their heads. Don't. There's no need. We've evolved. You have a machine that does something very simply. So we are now going to do what we know how to do is compute the empirical distribution of the statistic. Okay, so panel size, 1,453. We have to decide on the number of repetitions. I just chose 5,000 off the top of my head. When you run it, you can choose 1,000 or 10,000 as you wish, or any number that you wish. It doesn't have to be a round number, by the way, but we're just tied to round numbers. Okay, so we are going to collect all these total variation distances. We start by creating an empty array. Then for every single one of these 5,000 repetitions, we do what we did for our individual case. We compute the proportions from distribution and put that in a new table, and then we compute the total variation distance in that table between the eligible and the random sample. I would like you to notice something here. This is a piece of code that I have to write. I need to know the names of these two columns. Eligible, I know. That comes from my old distribution. Where does random sample come from? From the function proportions from distribution. This column that it creates is always headed random sample. And because that column label is constant, I can refer to it in code. This is not a statistical issue, but for code, this is very important. Right? So proportions from distribution creates a new table which has this new column called random sample that contains your new distribution. Okay, so that is the code. I will shut up. I will have you take a look at it. The heart of the calculation is these two lines. This says repeat that. This says collect it in here, and all of this says display it in a table. I will pause and take questions about that code before we run it. Nobody ever has questions about code. And then they come to my office, and it's like they're seeing code for the first time. Right? So actually go through character by character on the code. Do you understand why there's a comma in some place? Do you understand why there are quotes somewhere? The colon. Anybody, any questions at all? Yes. Okay, so what you're asking is not a question about code, yes? Just hold on a second. I will come to the question in just a moment. Questions about the code, the lines of code that are here. Nobody has any questions. Somebody has a question there? Move your arm. Ah, yeah, thank you. Yeah. So I need to collect my data somewhere and have it available for me at the end, right? So if my table creation is in here, yes, that table will be created for every repetition. So for every repetition, I will start out with an empty table, but I don't want to do that. Right? At repetition number 10, I want to start out with an array that has the previous 9 in it. I don't want to wipe it out by creating a new empty table. That's the reason for keeping that table outside the for loop. Yep. I don't want that TVD to be created every single time. I want one place where I collect the answer every single time. Okay, so the question here was, can we discuss why, just the conceptual idea here, why are we sampling from this 1,453 times? Because we are trying to compare this panel of 1,453 people with a random sample drawn from this population. You know, I think from previous discussions, that variability in a random sample depends on the sample size. Yep. So it is very important that the two sample sizes are comparable. And that is why our random sample size has to be exactly the same as the size of their panels. Does that address your question? Okay. More questions? Yes. The for loop ends when it comes to the last repetition. So this is an array here. It is 0, 1, 2, 3, 4, up to 4,999. Right? Once it has done number 4,999, it's just done. It breaks. All done. Yep. The function inside the for loop has to be indented, yes. So there is somebody in Python called a benign dictator who insists on that indentation. I actually rather like it. I'm perfectly happy to follow that rule. So when you do a for loop and you hit the return after the colon, it automatically gets indented. More. Table TVD function, what does it take at input and output? It takes the name of the table, the label of the column that contains one of the distributions, and the label of the column that contains the other distribution. So when we called it here, we were calling it on this table, which is called panels and sample, on eligible versus random sample. And so that is the call here. Name of table, first distribution, second distribution. More. This is exactly how, thank you, you should be looking at code at this stage of the class, yeah. Okay, good question. Proportions from distribution, how exactly is the sample drawn? So you see this distribution of eligible population, right? You should imagine yourself. The precise mechanism is not what I am describing, but it is equivalent to what I'm describing. Imagine that these are 100 people, 15 of whom have this label, 18 with this label, etc., etc. Yes? So you have 100 people with the right number of each label. If you used np.random choice, yes, you could draw 1,453 times at random with replacement from that population. That's what it's doing. Right? So it will end up with 1,453 labels, some of which are in this category, some in this category, some in this category, and so on. Yep? So it's as though it has got a new panel of 1,453 people. And now imagine using group to count the number in each category. Yep. And converting all of those numbers to proportions out of 1453. You know what? So when I wrote this function, I used a selection method that you don't yet have. So I think that is the best way for you to imagine. Actually create the array corresponding to the eligible jurors, sample at random with replacement from that array, and then compute the proportions in the different categories. That's what it's doing. So perhaps a question that may be occurring to some people is that it's sampling at random with replacement. Should you not be sampling without replacement? Right? You can get the same person twice. Well, you can get the same person twice in panels. But however, our reason is more numerical than that. The population of eligible jurors is very large. It's in the millions. Compared to that, 1453 is very small. When you are sampling a small amount out of a huge population, it doesn't matter much whether you're sampling with replacement or without replacement. Because you don't change the composition of the population very much by taking out a tiny number. And with replacement sampling, it's just easier because you're just doing it every time from the same thing. Right? So we are going to be using this approximation over and over and over again. More questions. This is all very good stuff. And I know we want to get to the end of the story, but it is important to know what's going on in the story before we move forward. All right. Anybody with an arm? Move. Some I'm seeing. Yes. Thank you. Thank you.
So does that mean for proportions from distribution, the column that it's sampling from has to be like
Does that mean that this column has to be in proportions as opposed to counts? I'm going to ask you to keep it in proportions. I believe the other will work as well. But what I implore you to do is to check that you actually have a distribution, that you have 100%, you haven't left anybody out. Right? That is why we are actually insisting that you have proportions in there. More questions? All right. So now we are going to run this thing, and I've kind of lost my place here. Okay, here we are. So we're going to simulate the total variation distance between our eligible population and a random sample from it 5,000 times, and we're going to look at the result. Here we go. Done. That's how long it takes. And here are the first 10 of the TVDs. So these are variation distance between eligible and random sample number 1, random sample number 2, random sample number 3, etc., etc., etc. Look at those numbers. They vary. Yes, they're not all the same. But do you see a 0.14 among them? Do you see anything close to a 0.14 among them? Not yet, but maybe it's hiding in the other 4,990 whatever. Okay, let's draw a histogram. All right, so what's the variable here? Total variation distance, yes, but between what and what? Eligible jurors and a random sample, right? All the actions down here. Where was the measurement that we got from the actual panels? Here. Okay, so now we have a decision to make. We have data. Which are our data? Our data are the actual panels. This total variation distance of 0.14 that we got there. We have what random sampling would predict. Where is that? That's all the way over here. Question for you. Are the two consistent or inconsistent? They sure look inconsistent. Now, there's an issue. Maybe you would have got something out here had you done more repetitions. You're not seeing this in your 5,000 repetitions, but if you had done 50 million repetitions, maybe you'd have got one. But at this point, your gut is saying, yeah, maybe you'd have got one, but you wouldn't have got too many. Yes? So you're saying that with high probability, a random sample wouldn't have given you a 0.14. That's what you're saying. You're not saying it's impossible. You're just saying that if you sampled at random, you're unlikely to have got the panel that they got. So now you have data, your actual panels, you have a theory. Sampling is done at random. When the data and the theory are not consistent, one of them has to go. Which one has to go? The theory. No matter how you are attached to it, it's the theory that has to go, right? Because the data are truth. Okay? And so what you have seen is that these are not drawn at random. However, we have not concluded why they were not drawn at random, nor have we discussed the implications of what this means. There is a significant discussion to be had about that, which we will have on Wednesday. And then this is an instance of a general way of making decisions, which will be the subject of Wednesday and Friday.